This video will be an introduction to proof by mathematical induction. The method of proof by mathematical induction is only valid for statements involving natural numbers. The natural numbers would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. You would not include any numbers that would include decimals or fractions or radicals or anything of that nature. Another name for the natural numbers would be the counting numbers. The principle of mathematical induction is based on two conditions. The first is you need to prove that the statement is true for the natural number 1. If condition 1 is met, and we'll call that the anchor or the base case, then you should move on to case 2 or condition 2, and that is you can make an assumption that the statement is true for some natural number k. And if it is true for natural number k, then you must prove that it is also true for the number k plus 1. If that can be proven, then by the principle of mathematical induction, your statement will be proven for all natural numbers. The structure we will use for mathematical induction proofs is first we will write the problem. The second step, I'll call it setting the anchor, and that is to prove that the statement is true when n equals 1. We may also interchange the term base case when doing the n equals 1. The third statement is called the inductive hypothesis. That's going to be an assumption that is made when n is equal to some natural number, and we'll call that number k. In the fourth step, we'll write a prove statement, which is simply a statement showing what you're trying to prove. And lastly, the actual writing of the proof, the strategy there would be to start with one side of the prove statement and then show, using your inductive hypothesis, that it is equal to the other side. You may have some question at this time as to whether this is a valid method of proof. I'd like to start with a counterexample to show you a case where the proof by induction does not work. Well, it shouldn't work in this case. 1 plus 2 plus 3 plus 4 ... plus n equals n. There's no way in the world, if you started with n and you added other numbers to it, that it should equal n. So let's show how, using mathematical induction, we can prove that this actually doesn't work. So for the base case, which is the anchor, we want to prove that this is true when n equals 1. So on the left side of the equation, we get just the number 1. On the right side of the equation, we need to plug in for n equals 1, and we see that 1. So actually our base case has been proven. At this point, we can go to the hypothesis, or the inductive hypothesis, which is assume that this statement is true when n equals k. So I'll write 1 plus 2 plus 3 plus ... plus k, notice how I substitute k instead of n, is equal to k. Now we're going to write our prove statement. We want to prove that this statement is true when n equals k plus 1. So on the left side, 1 plus 2 plus 3 plus ... all the way up to plus k plus 1 would have to equal, now on the right side, it would be k plus 1. Notice again that we substitute anywhere there was an n, we put a k plus 1. To write out the proof, we write out 1 plus 2 plus 3 plus ... plus k plus 1. Now if you notice, that is the same as the left side of my prove statement. However, I have highlighted 1 plus 2 plus 3 all the way up to k because that is the left side of my inductive hypothesis. So on my next step of the proof, I will substitute in the inductive hypothesis. The left side there is equal to k on the right side. So I'll substitute k for the inductive hypothesis, leaving me now with the statement k plus 1. When I combine like terms, I get 2k plus 1, which is not equal to the right side of the proof statement, which was k plus 1. Thus, 1 plus 2 plus 3 plus 4 plus ... plus n is not equal to n. So this shows that both cases, or both conditions, have to be met in mathematical induction in order to prove the statement's true.